Looks like we're live. Hello everyone and welcome to yet another Azuzin session. Let's make a little bit of an announcement and officially start the stream. Maybe, how about that? Red circle live on Twitch. And what are we doing today on Twitch a television website? Today we are doing HTML5 canvas-based UI in TypeScript. That's right. This channel is slowly descending into madness and we're becoming a web development channel. That's what we're becoming today. I'm gonna give the link to the place where we're doing all of that, twitch.tv/tsodin, and I'm gonna ping everyone who's interested in being pinged. There we go, the stream has officially started. So today we continue working on Autocell, basically like a small cellular automaton experiment that's been going on for several streams already, so it doesn't really sound that small, but the reason why it's going on for so long is because we're using web technologies. If I just wrote it in C, it would have been faster because it wouldn't have to deal with a lot of bullshit. Though, today we're gonna continue dealing with bullshit. Right, so essentially the idea is that we have a representation of a cellular automaton, right, and we are trying to take a pixel art image and turn the information within the pixel art image and information about the neighbors between the cells and stuff like that into a cellular automaton and see what kind of interesting behavior that may exhibit, right? Nothing particularly special, right? I'm not even sure if we're gonna end up with any interesting result, but developing this thing is kind of interesting nonetheless, right? You can find this the source code of this entire thing here. Right, so I'm gonna copy paste it in the chat, and for people who potentially watching that on YouTube, you will be able to find it in the description. I already put it in the description. Alright, so right now we have something like this, right? So here is the pixel art image, not by me, right? We stole it from the Open Game Art, and essentially what kind of cellular automaton we constructed out of that is basically we took each individual pixel in here, and for the frequencies of its Moore neighborhood, we created a state that basically refers to itself. So that way, when you take an image and put it on a board, this entire thing stays stable, right? It stays stable and won't you know, fall apart or anything unless you actually replace one of the pixels. As soon as you replace one of the pixels with, for instance, dead pixels or background pixels, the entire thing falls apart because this entire structure doesn't hold anymore, right? Because we constructed a cellular automaton based on the frequencies of known pixels. Right, and it's kind of cool actually. You can play with this entire thing, right? So I'm gonna copy paste it in here, right? But you have to refresh the page if you want to like, you know, refresh this entire stuff. It's kind of silly, but it's kind of interesting nonetheless. Right, it creates an interesting effect. Right, so yeah, that's pretty cool. I think so. There's sort of like a falling apart. So essentially what I wanted to do today, we have different states in the image. So essentially the way we work, we take an image and we analyze the unique pixels in that specific image, right? Unique pixels in that specific image. And the amount of unique pixels is the amount of states of that specific cellular automaton, right? So, and then we have sort of like a palette in here that allows us to draw different cells of different states. But unfortunately, as of right now, the amount of states for that cellular automaton is hard-coded, right? So you can only have dead and alive. It comes from the time when we were experimenting with just like things like Game of Life and stuff like that. So all of that is hard-coded. But depending on the cellular automaton, you can actually have different states. And I would like to reflect that somehow. So essentially, depending on the current cellular automaton, I want to have like different things in here. But also, since we are working with colors now, right, as you can see, these are colors, and there is no notion of dead cell, alive cell, there is red cell, there is blue cell, and so on and so forth, and all of the states are computed automatically based on the image. Like having names in here is not particularly useful, right? So they don't really tell us much. So what I would like to have instead is actually something like a palette. Right, similar to the palette you have like in my paint, right? So there are different palettes in here. So this particular palette is actually not kind of great. So there is a color palette. Yeah, I would like to have something like that. Right, So it would be kind of cool if we had something like that here on the side, and basically we had as many of these colors in here as there are states in this specific cellular automaton, so you can pick one and actually place it in here and stuff like that. So I can already place some stuff in here, but it's like a, I'm not sure if you can see that, right, but it's like a black color which is not background, so it's a little bit darker than the actual background, right? And if I play it, it just falls apart. Right, so I wanted to have something like this, but then how do I even code a palette like that? Right, how do I represent it in the HTML and stuff like that? Because I'm not a web developer, right? I'm not a web developer. I don't want to deal with the CSS or HTML5 and stuff like that. But then I realized, right, I'm a, you know, low-level C programmer, right? And how low-level C programmers do graphics? How do they do graphics? They just have an array of pixels and they just fill up the array of pixels. That sounds like a job for HTML5 canvas. Why not just create a single HTML5 canvas, which is going to be an element that implements this specific palette? So yeah, that's the idea for today's stream, right? I want to implement sort of like a widget, which is a single HTML5 canvas. And it implements behavior of this palette, right? It is going to basically accept the amount of states, right? And then each individual color of the state, right? And it will just like draw them, and it will handle the clicks on the canvas, and it will highlight the currently selected color, and it will allow you to switch between them and stuff like that. So it's sort of like a palette color picker, right? But we cannot use a color picker because we're not selecting colors. That's the thing. This is not a color picker. We're not selecting colors. We selecting states of a cellular automaton, and each state has an associated color. But we're not picking the color. Color is just a label on the state. Does it make sense? Right, so we're not really dealing with colors. Colors are specifically for a human being to make sense out of the state of the board of the cellular automaton. Right, so the cellular automaton doesn't care about the colors at all. It doesn't even know about them. Honestly, it really doesn't know about them. So as far as the cellular automaton concerned, it has states 0, 1, 2, 3, 4, 5, 6, and so on and so forth. Right, so it even in memory, it stores the states as the numbers, right? And then somewhere in a separate place, we have a table that associates, okay, the state 0 is transparent one, the state 1 is the black one, the state 2 is a red one. And when we're rendering the state of the board, we're mapping the numbers of the states to these colors, right? So because of that, it's not particularly color picker, but we're still going to make it look like a palette because that's what we as humans can interpret. Does it make sense? Hopefully that makes sense. So, and depending on the current cellular automaton, the palette is going to change, right? So because it's going to have different states, and correspondingly it's going to have different colors and stuff like that. So that's the idea for the stream. So. Hopefully I explained that well. So let's acknowledge some subs. Thank you so much, myc14 for Twitch Prime subscription. It was actually when I was offline, but thank you. And thank you so much, mycq, for Twitch Prime subscription 7 minutes ago. I really appreciate the Twitch Prime subscription. Okay, so let's go. How about that? I bet you're doing We're HTML programmers now. Yes. HTML programmers. So let me take a look. So we have div controls. By the way, this project is the first time I ever used Flexbox. I never actually used Flexbox before, and it's actually kind of convenient, right? So if we take a look at the CSS, right, so yeah, I set display flex on a class canvas with controls. Let's actually take a look at this class. Yeah, so basically whatever I put in here is going to be arranged horizontally. That's basically what it means, right? So it's arranged horizontally. So the first thing that is arranged here is the canvas itself, right? It's this thing. Let's wait for the, how is it called, DevTools, right? So this is the first thing. And then the next thing is the panel in here. So that's how it basically works. It's actually controls in here, right? So this is actually controls, and this is how this is where we have like a field set, and then the rest of the stuff. So I suppose for now I'm going to place another canvas in here. So this is going to be a canvas, and what this canvas is going to be, let's call it palette. Palette. How do you spell palette? I don't remember. Is it double L or double T? I can never remember if it's double L or double T. Freaking... Just give me the right answer, right? Okay, thank you. That's what I care about. All right, so we've got some subs. Would you look at it? Would you look at that? Thank you so much, Matt Kruger, for Twitch Prime subscription. Thank you with the message. HTML is poggers. HTML is the best programming language. Yes. Yeah, it stands for hyper transformative machine learning. That's what it said. Did you know that HTML stands for hyper transformative machine learning? So it's a machine learning language. Anyways, so we created a canvas. Yeah, it's a double T. Double T. Already forgot. What I want to do in here, right? So what's the width of the page in our specific case? I think it was. I set it to something like, yeah, 960. So the entire width is 960. And I set the width of the canvas, if I go to TS in here, the width of the canvas to 800. So that means we only have around 160 for the palette, right? And maybe this is exactly what we're going to set to, but I want to have some sort of a padding, so maybe because of that it's going to be 150, right? So that's the idea, so to speak. So let's go ahead and just introduce palette ID. So this is going to be palette, so I'm just going to be searching it within the DOM. So document get element by ID, palette ID as HTML canvas element. There we go. And this one is going to be palette. So this is the node. If palette is null, yeah, I'm going to be throwing an error. Throw new error. Could not find canvas. Palette ID. You know, it would be kind of interesting to maybe have a function, right? Get element by ID or fail, right? So here you accept an ID, and it usually returns, like in case of the get element by ID, it returns just HTML element or null, by the way, to indicate that you failed to get that element. We can try to maybe return some sort of like T, so you can simultaneously say to what you want to convert it to, what you want to convert it to, right? So, and also we're not going to be returning null, right? So there will be no, you know, or null. And in here, we're going to just like compress this entire pattern, because I keep repeating this entire thing over and over again, where I just like check for null and throw an exception. Maybe it makes sense to actually not do that anymore, right? So here we have an ID, here we provide the ID, so here we got a node, or maybe since the official terminology is element, right? So let's call it element because we're getting element by ID and we return HTML element, so it makes sense to call it an element. So if element equal null, we couldn't find element ID like this, and otherwise we just return something like this, right? So we do it like that. And because of that, I can probably compress all of this stuff to palette get element by ID, or let's call it error, right? So because here we're throwing an error, right? We're just throwing an error, right? So then I provide palette, then I say that I actually want HTML canvas canvas element, right? And it will automatically, so I don't have to do this kind of stuff anymore. Isn't that epic? I think it's pretty freaking epic. Right, so we don't have to care about null because it automatically just throws everything for us. Not sure how good of an idea that is, but it may work to some extent. So let me try to compile this entire thing just to see if it, you know, doesn't fail and stuff like that. So we've getting some subs. Thank you so much, Norn _ for community gifted sub. Thank you. Really appreciate it. Let me take a look. Okay, so we are returning. Oh yeah, you're supposed to return t, so we have to cast it as t. There we go. Okay, that's pretty cool. So it compiles, and as you know, if it compiles, what? It works. That's right. Kappa. Get element by ID or error, HTML canvas element, and we are accepting the app. Right, so we don't need that. Here we're instantly setting to 800, but here we're getting the context and we still need to actually, you know, check for that. We still actually have to check for that. So here we do next, get element by ID or error. This is next, but this is HTML button element. There we go. We don't need that. And I can even just copy paste this thing and just say play. And there we go. So that's pretty cool. So maybe it makes sense to actually find all of the get elements by ID. Right, all of the get elements by ID, and there we go. All right, that's pretty cool. I actually want to maybe move it somewhere outside of this function so it doesn't clutter the current scope. There we go. So we got another sub, actually. Thank you so much, Star Over, for tier 1 subscription. Thank you. Without any message, but for 25 months. Oh my god, thank you so much for such a long support. And welcome back to our epic web development club. We're actually HTML club right now. We're actually HTML club. Alright, so let me maybe start the HTML server. Right, not you can see that I'm not a web developer. Like, what's the? I need to start HTML server, guys. Like, yes, I'm starting the HTML server. Right. So I already have it started. Right. So I suppose I already like tested some stuff. Okay. Oh yeah. So because I demonstrated this kind of thing in here. All right. Seems to be still working. Right. So I didn't really break anything. Right. Yeah, there we go. So it works. Cool. Very cool. Let me find palette. So palette. So here we have a context. Right. So, and I actually just call it a generic context because I didn't expect that I'm going to have more than one canvas, right? So I actually didn't expect that. So maybe because of that I'll have to like use different naming and stuff. Palette ctx palette get context, right? So this is going to be 2D, and if palette context is equal to null, right? So like this, I will have to throw something like this, right? Could not initialize 2D context. And in here. Alright, one of the things I probably want to do, as already mentioned, by the way, is that I want to set the width to this thing to 150. Right, so essentially the entire width of the page is 960. We used 800 for the canvas, for the actual canvas for Cellular Automaton, and we only have 160 for the palette. Right, so I'm gonna account for a little bit of a padding if we want to add that, and actually make it 150. Right, I think it's gonna be enough for now. So, and after that, I'm probably gonna just like render fill style. So let's actually fill it with red. Palette ctx fill rect. Chat, do you feel rect? Oh, I'm sorry. Width, palette, height. Right, so we're gonna just fill the entire thing with red so we can instantly see the boundaries of this entire thing. Chat answers yes, same, for real, I can really understand you. Right, I also feel wrecked right now, especially I don't have any tea. I made some water right before the stream, right? I brewed some water. Okay, so, and because of that I feel kind of wrecked right now. Look at that! Isn't that poggers? Isn't that poggers? I think it's pretty freaking poggers. So this is the future canvas. Palette, not canvas, palette, right? So this is where we're going to be actually rendering all this thing. Right, let me see. I want to take a look at, is there any padding? Yeah, okay, so it actually said a little bit of a padding in here. So if I made it, for instance, I'm really curious, what if I made it not 150? Right, but 160, right? So let me see, what is going to happen? Is it gonna get, or is it gonna not change at all? I can't see shit. I feel like it didn't change at all, like completely. Something also broke somewhere here, so what the hell is going on? Can I just like this DevTools is so cluttered, I don't understand what the fuck is going on. Oh, it's just a favicon. Alright, so let me see. Oh right, so 160. I don't feel like it changed at all. There's still, yeah. Yeah, I think it's just like uses this as a logical size and it just crammed it as much as it could. So I don't think it matters that much. But I'm gonna make it 150 anyway. Hopefully that will make it a little bit easier to then, you know, parse or whatever. Okay, that's pretty poggers. I think that's pretty poggers. The HTML server should return favicon automatically. No, because we don't have a favicon, right? So unfortunately, and I couldn't be bothered to actually make one. I'm sorry. Right. So let me see. So what I need to do, essentially, I think I need to be able to handle clicks on this entire thing. So let's actually add event listener. All right, and when every time you click, we're gonna say something like console log palette has been clicked. Look at that. That's how easy it is to do web development without any React. You just get the DOM elements, you attach some listeners, and you're good to go. None of that React bullshit, and it just works. It just works. Okay, let's give it a try. So if I click in here and it doesn't work, is that because I didn't recompile or what is going on? The fuck? Can't fucking do it. Ah! It didn't work. Fuck. Oh, now it works. Right. I just forgot to recompile my dynamic language. Right. I forgot to recompile my dynamic language. Palette has been clicked. Okay, that's cool. That's very poggers, if I say so myself. So essentially, by the way, I want the palette to have a fixed amount of columns, right? So essentially, we're not going to adapt the amount of columns depending on the amount of states we have. We're going to say, okay, we're going to have this amount of columns, right? And if we have more states, we're going to wrap around to the next row, and so on and so forth. The question is, how many columns can we have? Right, so we have 150 pixels, right? We have 150 pixels. So let's actually factor out 150. So we have 2, 3, 5, 5. Maybe having 5, 2, maybe even 6. Right, so 150 is divisible by 6. Right, we can actually clearly see that. Right, if I divide it by 6, it's 25, so we can use 25 pixels. So we can say that we can have 6 columns in that specific palette. In this specific palette we have 7, right, in PyPaint, but here it is actually very easy to divide it by just 6. Right, does that make sense? Yeah, I think it's pretty good. I think it's pretty good. All right, so let me see. let's have some sort of a constant. Console, const, palette columns. Let's call it cols, and we're gonna have 6 of them. And that means we're gonna have a palette cell width, which is essentially palette width divided by palette columns, right? So this is the width of a single cell in here. So the thing I want to do in here, so let's actually first clear the rectangle, right? So we're gonna clear it. Is that a thing in here? Yeah, it is a thing in here, which is kind of canvas rect, huh? So, oh yeah, the rectangle render context just implements one of these interfaces in here. Okay, so that makes sense, sure. Okay, so then I need to take the current automaton, right? So I think the current automaton is the cute animation, cute automaton, right? So, and as far as I know, it's essentially, yeah. So let's iterate through all of the colors in here. So I'm gonna start with 0, cute automaton. It's an array of the states anyway, right? So it's an array of the states anyway. So, and I is basically an index, right? So I is basically an index, and we need to be able to convert it to rows and columns of the current cell. Right, we can probably quite easily say the row, right? So let's actually say that the row is I divided by the palette columns, but we have to actually floor this entire thing because by default the numbers in JavaScript are floats, right? So it doesn't have a, how is it called, integer division, unfortunately, right? So, and in terms of a call, it's actually I palette mod, right? But in case of a mod, is it going to work? I wonder. It's actually the state of integers and floats in JavaScript is sad and confusing. That's what I can tell you. It is sad and confusing. So for now, I'm going to just like print them, just to see what the hell they're printing. Right, I just want to see them. First of all, we probably want to go to somewhere here. What is it called? Autocell. Right, it's called Autocell. And I'm going to do node modules, bin, tsc, watch. There we go. So we're going to watch this entire thing. All right. So how can I learn about what current project is? Any command for that? There is a today command. Oh, okay. So the chat actually already describes. So yeah, if you're in the chat, you can always do the today command and you get the link to the current project. Maybe I could do a little bit better job describing what the project is in README, but it involves cellular automatons, right? So you need to know a little bit what a cellular automaton is, at least. Right. So that's essentially basically what we're doing. We're doing a little bit of a computer science in here. I'm sorry. Imagine clicking on the stream, thinking that this is HTML programming, and technically it is true, but we're also doing some computer science in here as well. All right. So, okay guys, so it will automatically recompile everything, so let me refresh this entire thing, and it seems to be correct, right? So, as soon as we have the 7th element, it goes around on the row 1, and what's funny is that if I don't do floor in here, will that work? That's a very interesting question, right? So I probably don't have to recompile, but I'm going to do that just in case. Right. Yeah, it's just like... Goddamn JavaScript, like it's so derpy. It's the derpiest language I've ever programmed with. Right, so basically you have two symmetrical operations, like division and mod. Right, so, but the division, since JavaScript doesn't give a shit about whether it's a float or integer, specifically for division, you have to do the floor. But because sometimes you need mod and integer mod, you don't have to do it in here. It's so freaking derpy. It's, oh my god. It's Anyway, I'm sorry. All right, so let's continue. Python is just better. It is. I do believe that Python better because it has a stronger typing. It is still dynamic typing. It is still dynamic, but it's stronger at least. I think you can use // command instead of floor. Can I? Is that a thing in Node? I don't believe you. All right. If I just divide this by 3, it's going to be that. Oh, they have integer division like in Python. I didn't know that. Okay, so, all right, they are slowly addressing the derpiness of the language, right? So it's like, the fuck is this shit? So, how do they even fucking tokenize that? So, wait a second. So, their tokenizer must understand the intent of the token to distinguish. Wait, am I being dumb? Because oh, I just... Who trolled me? Okay, so mods ban this person. Permaban. Who's that freaking... Okay, so I just remembered your... yeah, I just remembered your nickname. I'm gonna add you to my waiting ban list. So... Floor. I'm joking, I'm not gonna ban you. But it's actually kind of funny. It's funny that I fall for that. What the fuck? Like, my brain was rushing so much that I didn't even notice that it's not a thing. And it's just like, yeah, wait. So, and I just did that. And yeah, my brain just thought that it just contracted into a single number, but I didn't look properly what that number was. Yo, that's a perfect trolling. Holy shit. Okay, I can respect that. I can respect that. Anyway, so in any case, we have to do floor in here, right? And so, but this works, right? Okay, so now we have the coordinates of all of the cells, so we can actually draw them, right? Can't we? So row is actually y, and column is actually x. So essentially what we can do, we can do palette ctx style fill. I think it's a style fill or fill style. Fill style, and we can do cute automaton I, and I think, yeah, we do have associated color of that specific state. We set it as a fill style, and then it allows us to do ctx fill rect, right? And we fill an x, y, but we have to multiply it by the palette cell width. And I think I'm going to be making them square, which means that this specific thing should be probably size. It should be probably size, not width. So this is a size. Right, and then I'm gonna set this entire stuff. I can't see shite in this mist. Can't see scheisse in this mist. Okay, so that's a little bit better. So that will automatically populate like all of these rows, hopefully. So we're about to find out. Look at that. Here they are. Here they all are. Right in here. Isn't that poggers? I think it's pretty freaking poggers. So we can actually add more states in here. We can try to add more states in here. So essentially, the actual image that we're processing in here, right, the actual image that we're processing in here is this one. So just a second, I'm gonna do something like this. Right, it's this one. So what I did, I basically cut out only this image and I process only this thing. But we have more, right? So which actually has more different colors in here, right? So to do that, it should be relatively easy. I just added a couple of parameters to the transcendental adhesion of image. So that's the process of preparation the image for converting it to cellular automaton, right? It's called transcendental apprehension of the image. So I added a couple of parameters that allow you to specify the rectangle for the transcendental apprehension. And I only specify the size for that specific character. But then we can say, okay, use the entire image for the transcendental apprehension, and it will work. So yeah, welcome to the HTML programming stream, by the way. So okay, and let's refresh this entire thing. And as you can see, we have more characters in here, and furthermore, in the palette we have more colors, right? Because they are populated automatically. So this entire thing, whatever we have in here depends on like how we processed all of that. And as far as I know, like destroying all of these characters will also work. Yeah, there we go. So you can destroy them individually if you want to. Right. So what's interesting, there's so many combinations of black cells that it's virtually indestructible, right? So there's too many of them, they're very stable, right? But this one's actually, that's basically what we have in here. So, and I want to be able to actually click on those things and select the current colors, so to speak, if you know what I mean, right? Select the current color. So the way we actually do that in other applications is just we have some sort of a border around this entire thing, right? And maybe this is how we're gonna indicate the currently selected color for the palette as well, right? So the ninja is actually very resistant, but his face is not particularly resistant, right? Don't clip that out of the context, please. Right? Yes, it's actually quite funny, and it's kind of funny that it leaves the outlines of these things, right? Just leaves the outlines. Anyways, right. So we need to have a variable that keeps track of the currently selected color. I think we also have got some subs. Actually, one sub. Thank you so much, Atomata. That's exactly what we're doing, right? Thank you so much, Atomata, for tier 1 subscription. Thank you. Right, so actually pretty cool. So let's say that the currently selected color, right? So current actually state, right? As I already said, is it's a state. It's going to be like this variable. It's going to be a very simple variable, current state, right? So it's going to be 0. And how we're going to be like basically rendering all of that? How we're going to be rendering all of that? Well, here we render the cell, and if the I, right, I is the current state, we have to draw additional stuff. We have to draw additional stuff that indicates that that specific color is the selected one, right? And how we can do that? I suppose we can just draw some, you know, border, probably. We'll see. So let me take a look at the palette. Palette. CTX, we have fill rectangle, but do we have something like stroke rectangle? Yeah, that's probably what we want. So we have a stroke rectangle, and essentially, what if I use the same thing in here? Right? What if I use the same thing in here? It's too big, honestly. It's kind of like too big. Can I simplify it? Like, it would be better if this entire constant was smaller. Palette size, maybe. So that's already a bit better. So I can put that in here. Right. So this is a palette size. Actually, not cell, but size. There we go. So this is a palette size. That's already manageable, which is nice. And we may probably have a very specific stroke style for this kind of thing. Palette CTX stroke style. Yeah, there we go. But what kind of stroke styles can we have? Canvas gradient. All right. So canvas gradient is add color stop. Okay, so this is probably not. We want canvas pattern. Set transform. Okay, so let me Google up this kind of stuff. So HTML5 canvas, stroke style, width, color. And let's actually use Google this time. So stroke style property W3 schools. Yes, W3 schools. So I suppose, okay, so we can provide the color, that is fine. Let's set the color to maybe white, all right, so because it can be very much visible on the dark background, right? So, but furthermore, what if I want it to be thick? What if I want it to be thick? Sorry. So there is a line width, all right. Oh, and this is how you set the gradient, right? So I remember that the stroke style was also accepting gradient and stuff like that. But ultimately, what we need in here is probably line width. All right, so let's go ahead and do that. So palette, ctx, line width, right? And let's say it's going to be 5. And let's see how it's going to work. All right, so we're going to recompile this entire thing. Probably not required because we already have auto recompilation. Right, and let's refresh this entire thing, and as you can see, look at that, it is actually, it looks good actually. I'm surprised. So okay, what if now I say that the current state is 1, right? The current state is 1. So this entire thing, this entire rectangle is going to move to the next line. Yeah, and it looks weird. It looks a bit weird. I'm not really sure why, but maybe this is because like how all of this works. Right, so the right side somehow thicker than the rest of the sides. How does that make any sense? Like, okay. So maybe, I don't even know how the thickness is computed in this specific case. Maybe one of the things I need to do, right, I need to have the thickness as a value here. Let's actually do the thickness. And maybe what I'm going to do, I'm gonna shrink this rectangle according to the thickness. Let's actually make it smaller, right, so because I'm going to be using that in the mathematical expressions. Right, so here is going to be thick plus thick. And to shrink it, we have to subtract thick from the size, but we have to subtract 2 of them. Right. So maybe that's how it's going to work, but it just depends on how exactly this thing is implemented. Right. So, yeah. This one is interesting. I see. So it actually goes inside. Because of that, it probably... Yeah, I see what's going on. It probably... considers the actual contour of the line the middle of the drawn line. So the actual line goes in here, and the thickness is basically spreading outwards from the contour. So this is probably how it's implemented. This is how I implemented the frame function in Olivet's, right? So for those who doesn't know, Olivet's is just like a graphics library that worked on some time ago. Right, so tsodin, GitHub, Olivet's. You can find this entire thing in here, right? If you're interested, there's links in there. I'm gonna give the link in the description as well, right? Olivet's was pretty sure to be big. And if we take a look at how it's done, right? So, so there are some tests for the frame. Yeah, here it is. Yeah. So there are some test cases which demonstrate the thickness. So they actually draw on the frame is the white one, and the red one is the actual contour that's like relatively to which it is computed. So here is a good example because it demonstrates the odd thickness, the thickness with odd amount of pixels. Right. So I even tested things like that. Like this entire thing is like pixel perfect. There's a lot of edge cases to make this kind of stuff pixel perfect, which is kind of fun, I think. Right. So, and it's actually super fun to develop this kind of thing. All right. So because of that, I think we just need to subtract just a single thickness. Right. So we're subtracting just a single thickness, and it looks like shit. Why does it look like shit? Maybe because we have to then subtract half of the thickness. Maybe that's the reason. Maybe that's what you want. Let's refresh. Perfect. Look at that. Look at that perfection. Look at that. It's just perfection in my opinion. We can make it maybe slightly less thick. Let's actually use 3 pixels. Let's use 3 pixels. I'm gonna refresh this entire stuff. and that's even better. Yes. So what I'm trying to achieve is just basically this thing to be with the like contained within the cell itself, right? So that's what I'm trying to do. So 5 web dev streams in a row. Maybe Tsodin got a Starbucks opened up nearby. No, all the Starbucks actually left my country, which caused the entire IT infrastructure collapse. So all right, let's continue. So I think like 3 is actually pretty good thickness. Pretty good thickness. So now the next thing we need to do, we need to handle the clickage, right? We need to implement the clickage. How are we going to be doing all of that? So what I'm thinking, right? So the current state is basically this. We need some function, right, that redraws the state of the palette, right? So let's actually do something like const redraw, maybe let's call it redraw palette. Right, so this is going to be something like that, and we're going to take all of the code, that is responsible for all of this stuff, and move it inside of the function, except the constants, because the constants are going to be useful for the click as well, right? Because we need to compute the coordinates somehow. Right, so this is the redraw the palette, and here we redraw the palette. So when we're clicking on the palette, we're going to be modifying the current state, right? So we're going to be modifying the current state, but we need to determine on which cell we're clicking, right? So that's what we need to do. So for now, I'm going to do the following thing. I'm going to basically increment it by 1 with a mode of cute automaton length, right? So it will scroll through, right? So because I want to see how it reacts to this kind of thing without actually implementing the handling, right? So I just want just want to test that, right? So we're implementing this kind of UI incrementally. Okay, so if I click on this thing, as you can see, it scrolls through these things. It just scrolls through them. It doesn't know on which I'm clicking, but it just goes through them, which is kind of interesting. We can already technically do the following thing. Every time I click on the board itself, what we're setting in here, we're just setting whatever is picked by the radio button. But we don't really have to, right? Because like understanding what is picked by a radio button requires for loop. We don't really need that stuff anymore. What we can say, every time you clicked on this thing, just set it to the current state. This is actually perfect. That makes it so much simpler. Holy shit. So it already works. So we don't need to do that. Yeah. Holy fuck. Using this kind of canvas-based widget actually simplifies the code. What the fuck? Yo, that's so good. Right. So because you don't need to deal, yeah, and the reason why it simplifies the code is because you don't need to deal with the web DOM bullshit anymore. It's just like you don't have to deal. Like you've got just a canvas with pixels and just do whatever the fuck you want with it. You don't have to deal with the DOM. Just render whatever you want, and it just makes it simpler. Right. So that's pretty cool. So what that means, chat? What that means? That means that I can already draw whatever color I want. I can already pick and draw with whatever colors I want. I can already do that. It's a thing. And then I can continue playing the Cellular automaton, but it dies obviously. Alright, but yeah. So it already works. The only thing that is missing is to actually pick the actual color that you clicked on. So right now it just scrolls through them, which is not particularly great, right? But right, we'll have to like determine on which cell we're clicked there. All right, so let's continue. Let's continue. So let me see. We're redrawing the palette, and what we need to do in here, right? So we clicked on the palette, and we need to determine the coordinates, right? So I think we have to take the offset x and offset y. Right, offset x and offset y. So, but here we're going to be defining by actually the palette size rather than the other things. So rather than cell width and cell height, palette size, right? So this is going to palette size, and this one is going to be the also palette size because they are square, right? They're actually square. We got some sub. Thank you so much, Trevius, for Twitch Prime subscription. Thank you. Your first subscription. Welcome to our epic HTML club. How about that? Right. So this gives us X and Y, but this gives us only row and column of this entire thing. Right. But the state is actually continuous. The state is actually continuous. So that means the actual state is we take the column, which is Y, and multiply by the palette columns, right? So and then add the x. So that gives us the actual state that we selected. But what that means you can actually select some of the states that are outside of the available range. So if you click here, it will select the state that is bigger than, you know, the size of the cute automaton, right? It's bigger than the size of the cute automaton. Right, so essentially we need to check for that, right? So if state is less than cute automaton length, what we're doing, we're setting that state to the current state, right? So we're just doing that. Otherwise, I suppose we're just ignoring it. And if we're ignoring, I suppose there's no need to re-render anything. We're gonna just like re-render only when we actually modify the current state. And there we go. So that seems to be working. That seems to be working, right? Hopefully, we'll see. Okay, so if I click here, look at that. So I can probably like zoom in a little bit so we can see Scheiße. So I can now select between these things. And this is purely canvas. This is purely canvas. Isn't that cool? Isn't that freaking cool? Right, so this is not a like HTML component or anything like that. It's just like a canvas, if you know what I mean. Just a second. Right, so this is actually kind of cool, and it makes it simpler, surprisingly. Like coding this kind of thing is much simpler than messing with HTML, CSS, and some other shit, right? So it's just like, yeah, super easy. The only thing that I lack in here is some sort of like a visual feedback that you can click on those things. I would like to have a similar rectangle when I hover over those things. Like in case of here, we don't really see that, but I want to be able to see that I can click on this thing. Right, so maybe this is something that we can do. Right, so if we do palette, add event listener, and we're gonna say a mouse move, and this is gonna be this thing, right? So this is a mouse move. And on each mouse move, we of course determine the state, right? And if the state is one of these things, this one is a little bit this one is a little bit So what I'm thinking is that we need to keep track of the state that is hovered. If you know what I mean. All right, so, and we're gonna use that state hovered state. So for now, I think I'm gonna say it's null, right? But the type of this entire thing can be either number or null, right? So we can do something like this. And if I is current, we're gonna do that. Then if hovered state is I, maybe we're gonna actually, you know, swap them so it's symmetrical to this thing. I can probably copy paste this entire thing in here, but instead of color white, we're gonna use color gray. Is that how you spell gray? I think. We can probably move the thickness up there and remove it from here. So let me see. Any point in moving all calculations to WASM? I was actually thinking about that. Right. So if we can come up with any interesting cellular automatons, right, generated based on images, we may try working. We may try working on processing bigger images, right? And then we'll probably need more computing power, and that may require moving some of the logic to WASM. Right. We'll see. So, for instance, we can move the actual next board computation, right? Compute next board. We can move the storage of the state of the board to WebAssembly memory, and the process of computing the next board to like WebAssembly as well. And the JavaScript side is only going to pull out the state, the render state of the board, and just display it through a canvas. But all of the computations, all of the number crunching is going to be done on WASM, if we really need to have that, right? So we just move all of the heavy stuff to WASM. But I'm not sure if we'll find anything particularly interesting in this specific project, but we'll see. Maybe we'll be able to find something. Okay. What do we do in here? Right, so essentially we have a hovered state, and what I need to do. When we're moving, we just found that we're hovering over some existing things, and that thing is less than one of these stuff. So we can just say hovered state is equal to the state, but otherwise it is equal to null, right? So that will mean that it's not going to render anything. It's not null, not true. Okay. All right, and do we redraw everything every time? I think we have to redraw this thing. Yeah, I think we have to redraw it, so I'm going to put it in here. Okay, so we've got some sub. At Actoni Barrietta, thank you so much for Twitch Prime. Thank you. Alright, so what the hell is going on in here? Declaration or statement expected. What? Did I forget to put some stuff? What? These kind of problems are the worst because you don't. Okay, so there's a problem with curly brace. I forgot to put a curly brace somewhere or close, but I can't see. Where did I forget to close or did something? What the fuck? No semicolon. No, it's not because of semicolon, but there's something more weird in here. I forgot to either open or close somewhere, and the compiler is not gonna tell me. Line 22. Line 22. Where? What? Where did you get line 22? Let's see, where's line 22? So we've got some more subs. Ninosaur, thank you so much for Twitch Prime. Thank you. Okay. This is so dumb. Oh my god. Like, it could have like at least give more information or something like that, just to help me locate this exact like place. This is bad. This kind of error reporting is so bad. Oh my god. Ooh, Jesus. Like, you forgot to put curly brace in here. Good fucking luck. Good fucking luck. TypeScript is not gonna fucking tell you where it's gonna. Oh, I don't know. It's closing something. I don't know. Oh, Jesus. My God. Okay. All right. I'm sorry. Let's refresh this shit. Look at that. So this makes sense. Is it even visible? Is it even visible? Right, but it gives sort of like a feedback, right, on what you can click on, right. Cool. I think it's pretty cool. So yeah, so that means, by the way, we can finally get rid of this sort of like a brush, if you know what I mean, right? So this sort of brush, we can finally get rid of that, and we're only gonna have like this specific palette and the buttons, right? So that's actually perfect. So let me remove your mom. I mean, that's the name of the field set, right? So it's called your mom. So we can remove that. And we probably need to remove everything related to that stuff, your mom. I don't think we were even using it in the JavaScript code that much. I don't think we were even referring to this kind of thing. Yeah, it will just work now. All right, I can pause. I can add some stuff in here. So we can actually draw with all of these colors if we want to. Right. So, and let's just play and actually destroy this entire thing. Yeah. That's pretty cool. Okay. So that's pretty progress. So what we effectively did, so we have auto-populated radio buttons based on the current automaton, and this is basically what we did, right? So this is basically what we did. We created this sort of palette that you can just use. So let's go ahead and go back to the original smaller image of one person, right? We did that. So how many columns we have? We have 4 columns. Right, so this is the 4 columns, and in terms of rows, we have 3 rows. Right, so we have 3 rows. And let's go. So here's that. And as you can see, the palette actually became like smaller, so it doesn't contain the other colors that you don't have. So if I put, yeah, it instantly disappears. So it instantly disappears because of the way we sort of like prepare a cellular automaton, right? We go through each individual cell, we look at its neighbors, right? We look at its neighbors, and basically for that specific state, if it has these sort of neighbors, it switches to that specific state as well. And if there's any other combination of characters, of states, and other combinations of states and neighbors, it actually falls apart. So that's why it doesn't really stay for too long. It only stays in this exact specific combination of states. So we can try to do something more stable, even more stable than it is, right? So for instance, if in that specific state we have these specific neighbors, we're basically keep staying in that specific state, right? So if in this state we have that, we keep staying in that specific state. So the initial expected, so basically the default state is 0, basically the background, the left top corner. What if we check the following thing? If you are in a state 0 and you have the same neighbors as the neighbors in some other states that we found, that we observed, right, and we never actually encountered that thing before, we're basically going to switch the empty state to that state that we're currently observing. Right, will that create something more stable? Right, let's actually find out. Kind of interesting. Triple equals, yeah. Huh. It's actually less stable, but it just like collapsed very quickly. Huh, that's funny. What if I pause and I add a bunch of different things? Right, so it's so cool that I can just like do that. And it all disappeared, so it doesn't... maybe we have to do some other shenanigans here. Yeah, the only stable thing is the black outline. So we can try to maybe actually... Yeah, we can actually try to go through all of that. That's actually a very cool idea. So essentially, if we observe this specific state, we're gonna do that for each individual state. So how can we iterate through all of these states in here? So it's gonna be I less than cute automaton length plus I. All right, and in here, if we encounter that, for that state, we just switch to that. That will include 0 as well, and the state itself, even for the situation when I is equal to the state. So it just basically includes all of that stuff. That's not a bad idea. That's an interesting idea. I wonder what it will turn into. So one cool idea would be to extract this state evaluation method to a text file so we can modify it on the fly by the eval. Maybe, I'm not sure. Ooh, that's very interesting. So if I have some other things in here, right? Now they still fall apart. I want to come up with something that it doesn't fall apart every time. Right, how can we create some... Yo! That's so cool. Okay, what if we... Wait, that creates such a cool effect, holy shit. Okay. So what if we start not playing? Right. So here we set the interval, so what if we initially start at null? What the fuck? Okay, let's also make it slower. Right. I'm gonna recompile. That's so cool. I could probably achieve that without several automatons, but that's kind of cool that it can still do that. So by default, it doesn't really play. So here's the next state, and the whole thing is just like they're sort of melting, and this residual thing like continues to. Yo, what the fuck? That's so funny. Cellular destruction, yeah. Cellular destruction. That's so funny. But when it plays a little bit faster, like 100, right? So if the period is 100, right? So just like. Cool. We're already streaming for 1 hour. Let me actually do a committee, right? Let me do a committee, and we're gonna make a small break. And after the break, I'm going to try to maybe play with more different ideas on how to automatically generate cellular automatons based on the images. Or maybe we can try like other images, right? Maybe bigger images and see how it goes. Right, make two cellular organisms fight each other. I wish I knew how to do that though. So that's the problem. All right, so right now what I'm trying to do, I'm just trying to procedurally generate the rules of cellular automatons based on the images. But the question is, what kind of interesting rules we can generate based on the images? Like, what can we find there? Right. So right now we're just basically looking at the current neighbors, expected neighbors, and just like trying to do something with that, right? If anyone got any ideas on what kind of, how can we procedurally generate some cellular automatons, feel free to actually suggest. Allow more neighbors combinations to be stable. Yeah, sounds like an interesting thing to do. But how though? We got also an interesting idea. Okay, so let me do a committee. Okay. Implement state palette instead of hard-coded radio buttons. I'm gonna push that right into the repo, right? So it's gonna be available in the repo. You can find the source code of this entire thing here if you are interested. So there's also automatically deployed on GitHub pages, right? It doesn't have a backend, and that's why it just like works. Though the GitHub pages haven't updated yet, so it's an old version, so it doesn't contain the palette or anything like that. Yes. Okay, let's make a small break. I'm gonna make a cup of tea, and then after the break, we're gonna continue. All right, so let's continue. Let's try to like maybe have more images. Let's try it on different images. So the image that we're testing all of that stuff on is rather small, right? So, and that's why it works fast. So the image itself is 64 by 48 pixels, right? So we just scale it up so much, right? But it's a very small image by itself, right? So if you take a look at the actual image of these characters, here they are. Can you see them? Right, so if I open the web application, so here are the characters, but this is their real size. Can you see them? It's like, you can see shit. But if you zoom in, so here they are. It's very small. So let's actually try to maybe use something a little bit bigger, maybe not that bigger. For example, kappa. Let's use kappa. Can I use kappa? Copy image address. Copy image address. So I'm going to do wget and o kappa png. There we go. We've got some a kappa. It's still small image, but I suppose it is bigger. No, it's actually smaller, surprisingly. Oh, let's use it anyway. So I'm gonna go to index. So here is the cute people. Might as well just do something like image path, right? Image path equal to this, and I'm going to comment it out, and in here I'm going to replace this entire thing with kappa. How about that? Isn't that a poggers? A poggers, I think it is. Absolutely poggers. There we go. Kappa has a very similar colors, yes, but if they are different, they're going to be considered different states. So that's what's interesting about that. Yeah, so here's how many states we have in here. So, which also probably means that some of them are not fully visible, which raises the question, okay, so let me maybe adapt some stuff. So let me see. It's actually kind of cool. So this is a huge kappa. At the same time, you can even draw in here, right? So we can remove some of these things, like so, right? But this is a real kappa. So the next state of this kappa, nothing really changing, right? So let's actually keep playing, and let's remove, and kappa is disappearing. That's a funny one, right? Rest in peace, kappa. So what I need to do, I need to double check that we can even fit all of that stuff in there, right? So we set the width to 150, right? But after that, we need to know what we can do. So cute automaton, right? Automaton. We take the length, and we need to divide this entire thing by the palette columns, and that gives us the amount of rows. We have to also do math floor, of course, because we don't have a you know, integer division, and this is not an integer division. We already know that, right? So this gives us the amount of rows. If we multiply this entire stuff by this size, we'll get the height of the palette widget that we have to set to accommodate all of them. That's how we do that. That's math, isn't it? Well, it's more of arithmetics, or maybe even geometry, but I mean, nothing special. It's a very small subset of math. All right, so I wonder if that will actually increase the entire thing. Yeah, there we go. So this is how many states we have in here. So it has a lot of similar gray states. So that's why I wanted to do that, because I knew that it probably cannot accommodate all of them. Which also means, by the way, that if we have too many colors, all of the controls for this thing are actually down below, which is not particularly convenient. Seal, yeah, maybe I need to do seal, by the way. That's actually a good point. Yeah, I think something like seals is like will fit, because we're gonna have a remainder and we have to extend it to accommodate that remainder. Okay, thank you. So maybe we're actually missing one of the things in here. Do we? Let me double check, because it's too even. Yeah. So we're missing some remainder, and as you can see, there's like an empty thing in here. Thank you so much. All right, so this is not particularly convenient because all the controls are down there. So one of the things we probably want to do is to go here and take all of the lebatones, and move them in here. Might as well even put them in a separate div, just in case. All right. So here are lebatones, and there we go. So this is the next. We compute the next thing in here, and it just like disappears completely. There we go. That's pretty poggers, isn't it? I think that's pretty poggers. Cool. So let's take a look at some other images, right? Let's take a look at some other, maybe even bigger images, something like tsodinPog. So let's actually do tsodinPog. Can I download? Copy image address. Image. So this is version 2. Can I have version? Yeah, let's try to download that. tsodinPog PNG. Not hat. Wget. Okay. So we'll get that, but it's rather small. 56 by 56. Should be fine. On load, where is on load? There we go. tsodinPog. Oh, this is not what I want. What I wanted is just like rebuild this entire thing. Yo, what the fuck? Why? I mean, didn't I? All right. I thought, actually, this is not supposed to be like that. It's supposed to adapt. Yeah. It's supposed to adapt the height to this entire thing, and it's just like it shouldn't be like that, for sure. For sure. tsodinTol, yeah, exactly, tsodinTol. That is weird. So maybe something cached in there, or maybe something else, because I explicitly wrote the code that shit like that should not happen ever. But it still happens. So canvas is constrained horizontally. Yeah, I know. So because of that, I actually do app height, where I take the current board height divided by the current board width and multiply it by that, which is extremely weird. Alright, so let me take a look at the console logs in here. So we do a lot of console logs in here that are not particularly needed, right? So they're kind of distracting, in my opinion. Right, let's refresh that. So that's cool. So let me maybe take a look at this value. I just want to see. It's 1. How is that? Alright, so they only can be 1 when they're equal to each other. Alright. (56 by 56). That is true. So that means it's 1, and that means we're setting app width to itself. Right, so if I take app, maybe width, is that something I can do? Yeah, app height. Yeah, it is correct. Is the palette forcing the height? Ha, it might be. Okay, we're using Flexbox. Is there any way to tell the Flexbox, bruh, don't force this thing? Flex items stretch by default. Okay, so how can we not stretch it? I see. So that explains it. Well, we learned something. We actually learned something. So I'm using... God damn it. So Flex is supposed to like solve problems. Why is it creating more problems? Maybe I just don't know how to use it. Right. All right. Okay. So how can I just tell it not to stretch? Let's ask chat CCP flex grow 0. Doesn't tell me anything. You guys just throwing stuff out of the context. Okay. All right. So let's actually. Oh, probably. Yeah. Okay. I have two elements in flex. So let's actually in a container with display flex two HTML elements. How can I make the one not to stretch the other vertically? Okay. Prompting engineer stream. Yes, I'm a prompt engineer. Generate the code already. Nobody gives a shit. Code. Okay, so maybe somebody gives a shit. Okay, so to prevent one HTML element from stretching another vertically in container with flex, you can use align self property on the element that you want to modify. For example, suppose you have two elements, element 1 inside. Alright, if you want to prevent element 2 from stretching element 1 vertically, you could add the following CSS to element 2. Align self flex start. So to prevent 2 from stretching element 1. That's really weird. I don't CSS is weird, not gonna lie, but yeah. So you're telling me that that will solve the problem, right? So you're literally telling me that that somehow solves the problem. It doesn't. It's a Chinese instance of ChatGPT, yeah. So this doesn't solve the problem. So I don't really see. Did it lie to me? I think it lies. So let's actually try to generate a different response. Align self. Okay, finally it at least gives HTML. Alright. CSS cool. Didn't I literally do that? Align items. I think I literally did that and it didn't work. I think. I'm like pretty confident. Though I can try to do that without inline style. Like I used inline style, so maybe that's why I didn't like it. Or something. Wait a freaking second. I have to do that on controls. Okay, so I see. So this is not an element of the flex control. This is the element. So that's quite important. Okay, so that makes sense. So let's actually put it in here. Style. Align self. Go align yourself. Oh, go align yourself. Oh. Alright, so is it going to work? No, it didn't. It didn't fucking work. But again, I didn't have dev tools. So you have dev tools. Right. So, but why does it say, right, to prevent from stretching child 1? So did it just lie to me and I have to actually apply this thing here? Did it just fucking lie to me? What a freaking... Really? This motherfucker lied to me. So to prevent child 2 from stretching, this is child 2 and it was stretching it. You... Okay. No. You have to apply align self to child 1 minus what handed social credit. The future of programming, everyone. It still helped though, right? I should have actually googled it up. I think if I googled it up, it would be faster. Oh, the future of programming. The programmers are not needed anymore. Oh, oh. We're all gonna be replaced by Markov chains. Oh, oh. Sorry. Okay. AI is gonna end the world. Yes. Kawaii freaking this. So, well, yeah, okay, so I completely forgot what the fuck I was doing, yes. Right, so we got this, it's a tsodinPog, isn't it? I think it's pretty pog. Let me try to play this entire thing. Yo. It's especially funny that it's doing that from eyes. It's just like so cursed. What the fuck? So I think it doesn't do that with kappa. I'm pretty sure it doesn't do that with kappa. Right, if we just try to do the kappa. It is burning, yeah. Yeah, it doesn't do that. Yeah. The kappa is boring. The kappa is boring. The tsodinPog is kind of pog. So we're gonna compile this and everything, and there we go. There we go. Okay. So I've got an idea, actually. I've got an idea. So essentially, can I draw this entire thing? I want to kind of draw it. Imagine that we have a bunch of cells, right? So these are the cells. These are the cells. Right. So, and we're basically iterating through all of the pixels of the image, and we're analyzing the Moore neighborhood, right? So basically all of the neighboring things. And we notice that we have a pixel with a certain combination of neighbors. Let's say it's going to be like 0 to 1. And this pixel also have this combination of numbers, 0 to 1. But they have different colors, right? They have different colors. So, and what if we make an analysis? So basically some sort of like a table where we basically collect all of the colors that have that specific neighborhood, right? C1, C2, blah, blah, blah. Then we have another neighborhood like 2, 1, 1 or whatever. This is not like a real neighborhood or something like that, but we have a table, right? A neighborhood and all of its colors. And then what if we say, okay, if you are being in a state of C1 with this neighborhood, you switch to state C2. Then, if you are in state of C2 with this neighborhood, you switch to C3. And basically, for each of the neighborhood, we get all of the cores that we have in here, and we create rules that cycle through them. Does it make sense? That's an interesting idea. So what will happen? And we will take the image, we analyze all the pixels with all the neighborhoods, and we find the one that have the same neighborhood, and the pixels with the same neighborhood, let them cycle through themselves, right? What it will create, what kind of effects it will create, that's a very interesting question. I don't freaking know. Let's find out. Cycling rules, but that actually modifies, right? So this will modify the color, which will modify the neighborhood for that thing, so it will become different. So there might be some emergent behaviors that we don't expect. It's kind of difficult to predict what's going to happen if something like that happens, or if we code something like that. Right. So, but let's actually see. So we also have like more you know, images to test this kind of stuff on. Right, we have more images, but we're gonna start with the original one, with the original cute people. Original cute people. So these ones, which are basically just melting down right now. They're actually kind of cool how they melt down. Alright, so let me see. So, but I don't want to remove the current way of doing things, right? So essentially, I maybe want to extract this to a separate function, right? So we have a transcendental apprehension of the image, which just prepares the image. And here, we probably want to have a function that accepts both of them. Generate the rules. Right, and this thing is going to accept the board, right? So the board itself and automaton for which we are generating the rules. So automaton. So it's not going to return anything, but we are going to put this entire thing in here. So generate the rules. Cute board, cute automaton. There we go. And we may want to query replace cute board with just a board, and replace cute automaton with automaton. There we go. So let's actually see if this entire thing compiles. Okay, go. So it seems to be compiling. So, but though I don't really think generate the rules is a good name. So what we're generating in here is that, okay, we look at the pixel with a certain neighborhood, right? With a certain neighborhood. And yeah, I don't know. So maybe it's something like a Meltdown, right? So let's call it Meltdown. And this one is going to be Meltdown. Cool. So let's create a separate function for a different way of generating this entire stuff. Right? So we're gonna call it cycle rules. Right? Cycle rules, and we are accepting the same things in here. We're accepting the board and automaton. Right. So let's start iterating the board. Right. We're gonna iterate by rows, less than board height. ++ y, then we're going to be iterating the columns, x, x, width, x, there we go. And in here, we get x and y, so this is this specific cell. We may want to take the neighborhood, right, so the way we take the neighborhood is we provide the board, the amount of states we have, that's important, and the current cell, and that gives us the neighborhood key. Right, that gives us the neighborhood key. And we need to now have some sort of a table, right? Have some sort of a table. So maybe it's going to be neighbors states, right? And it's going to be an object that uses key, basically the neighboring key as the thing, and the value is going to be, I suppose, all of the colors that we encountered there. All right, so let's actually say that this is going to be an array. Actually, they're states, right? So that means it's going to be a number, the array of numbers, right? And initially, we're going to initialize this entire thing with an empty object. Okay, so now, so it's sort of like an inverse map, right? Isn't it? I don't know. Maybe it is. We'll see. Neighbors, neighbor states. All right, and we need to check. Do we have anything in these neighbors? Do we have anything in these neighbors? And if we don't, we need to initialize that with an empty array, which allows us then essentially push board get x and y. Right, so we essentially associate neighborhood with that specific color. And at the end of this entire stuff, we will essentially get, right, the, what is it called? The object which we can work with, right? We can get the object that we can work with. So we don't really generate the rules yet. Because that will require going through this thing and just, you know, adjusting everything. Right, so this is a cute board, this is a cute automaton, and there we go. Right, so let me recompile this entire thing. So we got some subs. So I think I didn't acknowledge them. Ninosaur, I think I already acknowledged you. A lifelong learner, thank you so much for Twitch Prime with the message. Thanks for having fun with us. You're welcome, I suppose. Thanks for watching. UC10, thank you so much for tier 1 subscription. Thank you. All right. So I think I'm in the wrong place. All right. Okay, so the reason why I want to run it right now, because I want to take a look at the log, and I hope to see the actual table that give us the insight into what is going on. Yeah, there we go. So let's, you know, unfold it. And here they are. Right, so basically with this specific neighborhood, we have things like this. Right, so, and as you can see, we have repeating things in here. And I suppose one way to combat that would be probably use the sets. Right, it would be better to use the sets. So maybe that's precisely what I'm gonna do in here, in fact. Right, so what if I replace this entire thing with a set of numbers? What kind of things do we have for the sets? You can append, you can delete, clear, you can do for each. That sounds good, actually. So here maybe I can just do set number new, and instead of push we do add. I think that's how it works. So let me see if it's going to work or not. So JavaScript has literally sets. Isn't that powers? I think it's pretty freaking powers. It even displays the different sets and stuff like that. There we go. So now we have unique scores, and yeah, so we can create a thing that cycles through that. Right, so if you have this neighborhood, it's going to cycle through these things. It's pretty cool, I guess. Maybe. So that was relatively easy to actually build, I think. So, okay, we've got that. So the next thing is going to be like iterating through all of these things and actually building the rules. It's like lists. Yeah, I mean, it's a TypeScript, right? So essentially in TypeScript, you can define types with generics, right? So this is a generic. So TypeScript is like a Java, but for JavaScript. Yeah. TypeScript is a Java for JavaScript. So yes. Okay, let's iterate through all of that. I want to iterate through, I suppose, the keys. All right, so we're gonna have neighbors, neighbor of object keys of neighbor states. Right, there we go. So this is the neighbor, and right, and for that specific neighbor, we're getting the states. Right, so this is going to be the states. And what we need to do, we need to iterate through them, right? So I think set had for each. Yeah, it has a for each. So that means we can just do states for each state, right? So this is the state. There we go. And what we want to do, right? For cute automaton, Qt atomaton at the state, right, at the state. In the neighborhood, so, and we can take a look at the transitions, right? So, and the neighborhood is this thing. We have to transition to the next one. We have to transition to the next one. But this is not particularly convenient because I cannot take the neighbor of this thing, unfortunately. So how can I convert the state, set to list? Let's go back to this liar, right? Goddamn liar. All right. So how do I convert set to array in JavaScript? Hello. Array from. Okay, thank you. I don't need to actually read the rest. I just remember that it is a thing. Array from. Yeah. So array like. So it means I can do array from. Yeah. It would be kind of nice if like these kind of chat systems actually had some preferences and they, or maybe something similar to I feel lucky, like in Google. So make it respond with like a single sentence. Like I asked, how do I convert? And it would answer array from, and that's it. And it would shut up. That would have been perfect, actually. Don't you think? That would have been kind of cool. It's just like a chat system that doesn't explain you shit specifically for programmers. It's just how do you do that? Just the array from, and that's it. And only when I ask what is that, only then go and explain what the fuck it is, right? Right. You can probably prompt it to do that, which it will forget in 2 messages. Yeah. So. So let me see. We're gonna have something like this. So this is the states. So that means I can. Yeah, I can just probably do something like this. And what we're gonna be doing here? Let I states length plus. Right. So the first state is going to be state 1 states I. The second state is going to be +1, but mod states length. So it will wrap around. It will wrap around. It's not poggers. I think it's pretty freaking poggers. So that means in here, if I'm in a state 1, encounter the neighborhood and border, I switch to state 2. That's it. So that's how we're going to be generating the rules. Right? So we collected all of the states with the same neighborhood, then we iterated through that one more time, right? And we just iterate through the states, and if in the state 1 we encounter this neighborhood, we switch to state 2. And since we're iterating by pairs, if we're in a state 2 and we like see the same neighborhood, we switch to state 3, and so on and so forth. And in here, we're gonna wrap around from the last state to the first one. Right. So that's pretty poggers, I think. So we're cycling through, and let's actually do console log Qt atomaton and see what kind of stuff it generated. I should probably rename, get rid of the like prefix Qt, right? Because we're not only using Qt people in here, right? So it could be any images in here, so we have to kind of abstract away from this kind of stuff. But anyway, so what do we have in here? 218. Did I forget to recompile? I think it successfully compiled, but we have a runtime error. Yeah, I didn't compile it properly. So what you don't like about that? What's wrong with that? Can't find name state. So. Alright, so what we have in here, so it's an automaton. What's the termination state? Is there any? Why do you need the termination state? The show must go on. Alright, so let's refresh this entire thing, and we've got some stuff in here. Let's take a look. Okay, so this is one of the states. Let's take a look at the state 5. What kind of transition? That's actually kind of interesting. That's a lot of transition if you ask me. All right, so in these specific transitions, we actually stay at state 5. The default one, what's the default one? I can't see. The default one is 0. Maybe we should set the default one to be the same as this state. Maybe that's one of the things we have to do. Right. But sometimes, as you can see, you may switch to 8, right? If you have this specific neighborhood while being in the state, you will switch to 8. It's doing some things. It's doing some things. Okay, so let's take a look at some other things in here. So when we are in 8, we can switch back to 5, sometimes to 10, right? Sometimes to 2. So as you can see, we have some transitions in here. I've just got an idea. What if, is there any theory on non-deterministic cellular automaton? Because this entire thing is deterministic, right? Having a certain state of the cell and certain neighborhood, you guaranteed to switch to that specific state. Can you have, okay, I'm in that state, I have this neighborhood, but instead of 100% switching to that other state, what if I had a table of probabilities of switching to different states? And you can build up that table based on statistics of several images. And then you put softmax on them and just like randomly pick. Yo, what the fuck? Is there any like a theory on this kind of automatons? I don't know. I'm not a computer scientist. I don't know. Like randomized automaton. Yeah, randomized automaton. That's actually very interesting. I don't know, I'll need to explore that idea. Because you can base that probability on some statistics that you collected on several images, right? So, and that basically turns into Markov chains, actually, if you think about it. Yeah, that's basically Markov chains. Right. Okay, so we've got this thing that's supposed to circle around, right? So it's supposed to circle around. Right now we don't run anything. Let's compute the next state of this entire thing. Okay. What's gonna be the next state? That's kind of cool. It doesn't really disappear though. Okay, what if I just try to play this thing? Well, I mean, that's kind of cool though. Yo, what the fuck, that's cool. I like that. Wait a second, what if I do that trick with 4 and 3? Alright, so what if I have only a single one in there? That's so cool, I like that. Okay, so we have this next. Yo! It's a cyclo. What the fuck? This is so fun. Yo. What the fuck? And then it just disappears, right? It's kind of surprising that... Yeah, it just disappears, but that's funny. That's kind of funny. Right. Yeah, it's an AI art. Yeah, that's what it is. It's an AI art. Yo, why is it so fun? I don't fucking understand. What's interesting is that I don't have any particular goal. I'm just fucking around, right? So it's fun, right? I think I'm going crazy. Is that the definition of insanity? I think that's the definition of insanity. That's for sure. Yeah. And disappears. Okay, so let's actually try some other cellular images, not cellular automatons, but images. Let's take a look at the kappa. Right. Definitely favors black, but this is because of the outline. We have too many combinations of outline, I believe. So if you take a look at this kind of thing, let me see, black, right. So yeah, so essentially there's too many combinations of this like black outline color, and because of that it's very stable, right? It is very stable. there's not that many like of green or blue or red combinations, and that's why they're not that stable. But there is a lot of example for the outline. So this is my hypothesis, at least. All right, so here's the cup. So let's see what it will turn into if we do something like this. It doesn't really turn into anything. So if I play, it doesn't do anything, and it just disappears. Probably because there's too many states in here. Right, yeah, there's too many states. If we look at all of these states, it's just like doesn't have enough combinations to be stable or interesting. So I don't think kappa is that useful for our specific case. So let's take a look at tsodinPog. All right, let's take a look at tsodinPog. Is the black the default to 0? No, it's not default. The default to 0, I think it's transparent. All right, so we have tsodinPog. tsodinPog. There's also, yeah, there's also too many combinations in here. I don't think it will anything useful. Yeah. Though, yeah, it ends up being like devouring this entire thing as well. Right. Yeah, I think the most interesting one was the cute people, because it's a very simplistic pixel art, right? It's a very simplistic pixel art. Yeah, we could probably pre-process the image to actually reduce the amount of colors. One of the things we could do for sure, just to have some interesting stuff. But this one is so cool, right? So the cool thing is that now I can just draw some stuff in here to get some interesting stuff, maybe. Right, and let's take a look at the... and it just disappears very quickly. Yeah. This one is cool. All right, so let me see. So this is just a cyclic rules. There was another interesting idea suggested, I think, by Kolombetka on the break. Maybe a cell could copy the state of its neighbor. This is a very interesting, actually, approach. Essentially, for each individual cell, right? So we look at the cell, at the current cell, and its neighborhood, right? We look at the current cell and its neighborhood, and we're switching to the state that has the most frequency, if you know what I mean. But that raises the question. Okay, so what if I have cell A with one neighborhood and the same cell A with a different neighborhood? Like to which I switch, because the different neighborhoods may have different frequencies. Like, how do we decide? We can just sum up the neighborhoods, right? The frequencies of the neighborhoods, and switch to the most frequent when like we sum up all of the neighborhoods. Does it make sense? We can try something like that and see what kind of like cellular automaton that will generate. Sounds interesting. Just cycle through. No, we already did cycling through. Like, I don't see how we can cycle through in here. Well, yeah, in that case, sum can be more than 8, but we're not going to be using sum as a key in the transition table. We're using it only just to make a decision on the rule. Right. So we're only making a decision on the rule. So I think that's going to be fine. I think. Okay, let's give it a try. So we have a cycle rules. Let's call this thing a frec rules, right? Frec rules. We're gonna accept the board and automaton, right? And go. So let's go. Let's start iterating by rows, of course. So this is gonna be by rows. Board height plus y. X width x. Okay, so then I do board. I think I need to do count neighbors, right? So what do we have in here? We have this kind of thing. So we take the board. The amount of states is the automaton length, and we just put x and y in here. That gives us the neighborhoods. Right, so this is the neighborhood. So one of the things we probably have to have is the map that maps the state to all of its neighborhoods. right? So because we just need to collect all of the neighborhoods. So here's the interesting thing. Here we had a map from neighborhood to the states, but this one is an opposite. We need a map from states to the set of neighborhoods, or rather maybe list of neighborhoods. Right, something like that. It's the other way around. Right, I mean, a neighborhood is actually a string, right? So neighborhood is actually a string. That's kind of interesting. So this one is called neighbor states, and here we have states, states neighbor, state neighbors, state neighbors. So this one could be something like this. All right, so let me see. So this one is going to be just new, state neighbors, and there we go. So how are we going to be doing all of that? So the reason why I'm using map is that because the JavaScript objects do not allow to use numbers as the keys. It will automatically convert them to strings anyway. All right. So let me see. So how do you use map? Can I check if a particular key exists there? Okay, so there is a has. So you can check whether it has a particular key. State neighbors has the state. Right. So maybe because of that we have to do something like state board get x and y. Right. So we've got x and y. All right. So, and what we need to check whether we have this state, right? If we do have this state, what we do, right, we just get that state. Though, interestingly, I suppose get may return undefined. Yeah, it can return undefined. All right. So that means here we get neighbors. Right, there we go. So we get neighbors, and this is where you can check if neighbors is undefined. Right, if neighbors is undefined, maybe it makes sense to set neighbors to new array. We're setting it to new array, then state neighbors add. How do you do add? Set, I suppose. Where am I? Okay, set state to neighbors, and then just do neighbors push neighbor. There we go. So first we're checking, does that thing exist within that? If not, we're just creating. And I basically expect that arrays are passed by a reference. So this is sort of like a reference value. Right, so this is basically what I expect in here. So, okay, let's take a look at the intermediate state and see what we gathered for that specific image. I'm sorry. Excuse me. So this is a cycle, frec rules. Excuse me. So cute board, cute automaton. Cute board, cute automaton. So let's take a look at the compilation errors. Okay, and let's refresh this entire stuff. So we've got some stuff. Look at that. Do we really have that many of these things? What the fuck? Are you telling me 1,000? Okay, that's one mention. Do we really have to do the... That's actually a lot. So that's specific. This is probably a black pixel, right? Yeah, it is a black pixel, I'm pretty sure. And this is all of the neighborhoods it was seen in. So, and do we want to sum up all of these things? I think we do, maybe. I think it makes sense. I think it does make sense. Though, how are we going to be summing up all of that? Right, so if I have a string, right, so let me actually explore. So if I have a string which contains numbers, right, so how can I get the length of this? Okay, so I can get the length of the string, sure. So that means I can iterate this stuff. Length plus I. Console log si. Is that a thing I can do? Okay, cool. But then I want to turn it into a number. Okay, so there should be a way. JavaScript string to number. Parse int. Okay, I can do that. Parse int. Yeah, that makes it super easy. Right, so you can just iterate them and then just parse int, and there you go. I lost memory now. You're welcome. So cool. We will need the following thing. Okay, let's start iterating all of that stuff. Can I iterate map with for each? Yeah, I can. That's cool. So state neighbors for each. But the question is, where is the... Okay, so the first one is a value, which is the states, and the key is the neighbor. It's a neighborhood in here. Right, there we go. So that means for that specific... Ooh, I'm an idiot. No. The first one is a value, which means it's neighbors, and this is the state. Okay. Oh god. Okay, so I need to create an array of the neighborhood frequencies. So that means I need to create an array of the size of automaton length. And fill it with 0. Right. And that will create the neighbors frequencies, I suppose. Right, so the neighbors frequencies. The next thing I need to do, I need to iterate through each individual neighbor of neighbors, right? Then I need to iterate. I suppose since the states, we know precisely the amount of states, I need to iterate through 0 to automaton length, right? And what I can do now is just basically neighbors frequencies I plus neighbor I, but parse int. Yo. Okay. So the next thing I need to do is that I need to find the index of the maximum frequency. Right. So, but how can I even do that? Right, so I can do max. I can find the maximum value, but I need an index of the maximum value. I need an index of the maximum value, which makes it kind of nah. Okay. So we can have something like an index, right, which is going to be undefined for now, right, and the max value, right, the max value. So we're going to be iterating through all the states, right, so we have all the states in here, yeah, I think I'm an idiot. This is not how we're supposed to do that. Yeah, this is not how we're supposed to do that. Yeah. This is completely wrong, right? Because I need a specific neighborhood, right? If I, right, so I have an automaton, some sort of automaton, and I'm in a specific state. To transition, I need a specific neighborhood key in here. And what kind of neighborhood key I have in here? I have nothing. So I don't even need any statistics in here. That's what's funny. I don't even need any statistics. What I need to do is for each state, generate all of the possible neighborhood keys And for all of the possible neighborhood keys, I need to switch to the most probable state. What's funny is that because of that, this sort of approach means that I don't need the board. So this kind of stuff can be generated just using Automaton. Right. And it has nothing to do with, it's not based on the images themselves. It's not based on the images themselves, but rather on the amount of states. Right. So it's based on the amount of states, purely. Yeah. We can try that. That could actually create a very interesting stuff. Though generating all of the possible neighborhoods is also a very interesting problem, right? Because you have to do that recursively, right? So you literally have to do that recursively. Yeah, so let's actually scrap this entire function. So this is not how I wanted to do that, right? So this is not how it goes. Definitely. And by the way, this entire thing should not accept the board, right? It has nothing to do with the board. It's just purely based on the states. It's just purely based on the states. I'm already streaming for 2.5 hours, my god. And I'm already tired, and I need to make a small break to continue with this idea. Right, I need to make a small break to continue with this idea. So maybe I should go for a break. Or maybe I should not go for a break. Let's actually go for a break. Alright, so we need to generate all of the plausible neighborhoods. How can we freaking do that? So the thing about neighborhoods is that they always have to add up to 8, right? There's only 8 neighbors. So can we have some sort of like additional example in here? All right, so create neighbors JS console log, right? So hello cman, right? Node neighbors neighbors.js hello cman. So let's say that I have only how many states? I have only one state, right? So in that case, the only possible neighborhood is going to be just 8, right? So yeah, so you can have only one state, and for each cell you have 8 of the same states, right? Let's imagine that you have 2 states now, right? You have 2 states now. How many plausible neighborhoods you can have? Let's actually brute force them literally. Right, so you have the first state, right? So let's actually call it maybe A, and A iterates from 0 to 8, right? So it might be equal to 8 as well, right? Plus A, right? And the second state is going to be B, right? So essentially, what we want to say, if A plus B exactly equal to 8, that's a plausible neighborhood that we may have, right? And we're going to just print it, right? We're going to simply print it. So this is going to be A and B. So let's go. So these are plausible neighborhoods. All of them add up to 8. So if you have 2 states, you may have 3 of the first state and 5 of the second state. Right, you're never gonna have 3 and 4 because they don't add up to 8. Right, you can have 4 and 4 and so on and so forth. So effectively, if you have 2 states, you may have 9 possible neighborhoods, right? And this is what the binary string basically means. If you see the neighborhood is a string, or not binary string, a number string, this is what it is, right? If we join this thing like that, that's basically the neighborhood key. Right, the amount of characters in neighborhood key is the amount of states in here. So that's basically what it is. Right, if you have 3 states, for instance, all right, so we're gonna have C in here, and then do something like this, and C. So how many of them are we gonna have? So these are all of the possible neighborhoods. In that specific case, we have 45. Right. So in case of one state, we can have only one neighborhood key, which is 8. In case of the 2, we can have only 9. In case of the 3, you can have 45, right? So I think it's 45. Yeah, 45. 45. So what do we have? 4 of them. Right, something like this. So it's actually very easy to add them up, right? So you just add additional, you know, for loop to generate this kind of thing. So in case of the for, how many of them are we going to have? Right, so let me see. It's 165, right? 165. Which forms a very interesting sequence. Like, what the hell is 1, 9, 45, 165? So there is a very interesting website actually. Database of number sequences. Database of number sequences. It's called oyeah.org. That's literally how it is pronounced, right? So online encyclopedia of integer sequences. Let's take a look at it. So the cool thing about this website is that you can put any sequence in there and it will search it and it will tell you what is this sequence. So the next value is supposed to be 495, right? And this thing is a figurate number based on 8-dimensional regular simplex. Isn't that interesting? So it's a binomial coefficient with 8. So it's a binomial coefficient with 8. What's interesting is that if we add another state in here, theoretically we should have 495, right? So let's actually give it a try. So E plus E, this is going to be E, and something like this. Okay, so we have 5 states in here now, right? How many of them do we have? Look at that. It is true. Right. So this kind of website is really cool for finding different like relationships between different processes and stuff like that, right? So, and it already says that it's basically a binomial coefficient, right? So this is basically a binomial coefficient, and binomial coefficient actually describes the Pascal triangle, if I'm not mistaken, right? So essentially, binomial coefficient has 2 variables, right? And one of them describes the like a row or column or something like that. I don't quite remember. But if we try to Google up Pascal triangle, right? So the Pascal triangle. Let's actually find a big one. Is there any like a big one, really big one? Yeah, there we go. I think that one is good. Oh yeah, here it is. Look at that. So this diagonal 1, 9, 45, 165 to 495, right? So it's basically binomial coefficient. It's that specific diagonal on a Pascal triangle. Right? Isn't that cool? Right. It's like you wouldn't expect that these things somehow related to like binomial coefficient or something like that. By the way, I knew that up front because I was researching how to do like different representations of this sparse matrix for transition tables, and I was just like seeing, can I predict the amount of states that I need, and what's the formula that predicts the amount of states? And this is what I discovered. It's literally binomial coefficient, right? It's just like something that I wanted to demonstrate and show. I think it's kind of interesting. Not sure how useful this is going to be for us, but I think it's kind of cool. So that's pretty poggers. I like how it looks accidental. Yeah, it does look accidental, but at the same time, I think it kind of makes sense as well. I think. But yeah. So what I was doing, right? So essentially, the reason why I need all of that, I need to generate all of the possible neighborhoods. So, and since the amount of states may vary, the amount of nested loops may vary as well, right? So essentially, we have a variable, not the amount of iterations, but actually the amount of nested loops. So the amount of nested loops is the variable that we have, right? So if I have 5 states, I literally have to have 5 nested for loops. How can you achieve variable amount of nested loops? Well, one of the things you can do is you can watch one of my videos on the topic. Right, so let's actually find out. Let's actually find this kind of thing. Let's wait until YouTube actually loads it. Okay. Tsodin infinite nested loops. I literally have a video on that. Believe it or not. Infinitely nested loops. That's a title I'm really proud of. Like, it's just such a cool title. Look at that. You won't like. By the way, small behind the scenes. So essentially, the ratio between the size of outer loop and inner loop is a golden ratio, right? No joke, really. So basically, I did that in Inkscape, and I took width and height of this thing, and I multiplied it by a golden ratio, actually inverse of the golden ratio, which is 0.6 something something, and I got this thing, and it fit perfectly inside, and then I multiply it again and again and again, and that's why it looks so good, because this is literally a golden ratio, like literally golden ratio. I literally took the constant and multiplied the size. So yeah. So essentially, in this specific video, I describe that you can achieve infinitely nested loop through recursion, right? Because it's you basically have a for loop, and in the for loop you recursively call itself, and it infinitely nests the loops, right? So you can watch the video in here, right? So I'm gonna copy paste it in here, and I'm gonna also put that in the description for people who maybe eventually watch that on YouTube. Infinitely nested loops, right? This one's it. It's a very short video. It's more of like it's something in between of a small educational video and a shed post. In fact, I kind of intended it as a shed post, right? It feels like a shed post, but at the same time, it has some interesting food for thoughts, right? So it's an educational shed post. That's what I like to call it. Right. Education through shed posts. I think it's a pretty effective way of educating people, in my opinion. Anyways, so let's actually create a function, right? So recursive function that is going to be generating neighborhoods, right? So, and in here, I suppose we're going to be generating the states, right? So here we accept the state. Since this is a JavaScript, it's not TypeScript, I cannot provide the types. It really is KEKW, so it does feel like a shitpost. But at the same time, it is educational, isn't it? Because it allows you to look at the recursion from a different angle, right? So, because I've actually seen people telling me that they never thought about recursion as infinitely nested loops, but this is one way to look at recursion, right? So it's a variable way of nesting loops, right? So, and the shitpostiness of this video comes from the fact that a lot of people think that like a lot of nested loops is a bad idea, right? And I'm actively encouraging something bad. Right, I actively encouraging. I'm saying that nested loops is good. Nest as many loops as you want. In fact, you can have like infinite nested loops, and this is where educational value comes in. Right, it basically offers a different perspective on recursion. So it's a shitpost, but a shitpost with a twist that actually expands your mind. That's the content I subscribed for. That's what Tsodin project is all about. So, right, we've got some stuff. Thank you so much, Nevis 101 for Twitch Prime. Thank you. Right. So, yeah. And by the way, when I post my videos, I really do actually unironically think about things like that, right? So, my perfect content is a absolute shitpost that triggers people because it promotes some controversial idea of nesting a lot of loops, but at the same time it offers a different perspective that lets you look at things from a different angle. That's the content I like to produce. Like, this is content I'm striving for. Controversial, shitposty, but at the same time education. Yes, that's what I like. It's really difficult to produce such content, to be fair, right? So it's really hard to find this balance between education and shitposts. And sometimes my content is too educational, become boring, and sometimes it's too shitpost, people thinking I'm fucking insane. So striking that balance is actually really hard. Yeah. All right. So what I want you to do in here, right? So we are, if the amount of states that we want to generate neighbors for, right? So we're trying to generate the neighbors for that specific state, right? If the amount of states we offered to generate for is equal to 0 or even worse, less than 0, we say fuck you and we go out of the recursion, right? So if it's greater than 0, what we do? We do iteration, let a 0 less than 8 plus a, right? And essentially what we have to do, we have to call neighbors one more time with the state -1. And that what ultimately creates an infinite nested loop, right? So if we try to do neighbors, for example, 0, you instantly get fuck you and bail out. If you have 1, this entire thing is going to be replaced with just this infinite nested loop, but with neighbors equal 0, for which it essentially will just do nothing. If you put 2 in here, you actually increase the amount of nested loops, like so. Right now we have 2. So the amount of nested loops is how, like, what kind of numbers you put in here. You put 3 in here, you're gonna have 3 nested loops, and so on and so forth. Okay. So, but here's an interesting thing. When we have to check this specific condition, when do we have to check this specific condition? We have to check it when the state is equal to 0 or 1, right? So this is where we have to check all of that condition. But to check that condition, we have to have an access to all of the previous iterators that we had in a recursion, right? So we have to have an access to A, and then nested A, and so on and so forth. The question is, how can we access them? So that's a very, very interesting question, I think. So we can try to maybe push them into the in here, right? So essentially we're gonna have the I don't know, so axis, right? So this is the axis, and we're iterating x like that, all right? And essentially as we go further, right, so I just do push x, then I pass it further, right, and then when I'm done with that specific thing, I think I need to pop it out, right, and I'm not sure if that's how it works in Node.js. Is that how it works in Node.js? I don't know, right? If I have something like this, right, so this is just an array, and I push a 69 into that array, and I've got a 69, and then if I do pop, does it pop it out? It does in fact pop it out. Isn't that Pog? It's literally a stack. So we've got a sub from KMode9. Thank you so much for tier 1 subscription with the message tsodinPoging. Thank you so much. I'm also pogging right now. Can't stop pogging. All right, so that's pretty cool. So that means here, as we iterate through all of this scheisse, we do have these things. And it should be super easy to sum up all of these numbers. Is there anything like sum in here? Okay, so there's nothing like that. JavaScript sum numbers. Array of numbers. Oh, you can use reduce. Wait a second. You can have reduce, right? Reduce a plus b. Is that what I can do? Right? Oh yeah, okay. So let me double check. Yeah. Okay. can use that. So access reduce a b a plus b, and this is where we can check if this entire stuff is equal to 8. That's the thing we care for. That's the thing we care for. So we can actually, so this one iterates like the whole space of these things. We can implement some sort of optimization that doesn't go deeper in the recursion if the current state is already greater than 8 or equal than 8 and stuff like that. So there is a lot of like ways we can optimize that, but I'm not sure if I care about it right now. So if this entire thing is equal to 8, that means I can just like go ahead and literally print this entire thing, like access, right? If it's not, I just ignore it, right? And we just continue. And that should be it, I think. So that should effectively implement everything we want, right? So this one's going to be neighbors. Let's start with 0. So this thing should not print anything, and it doesn't even work. So what does it say? Cannot read properties reduce of undefined, and this is because we have to put this thing in here, I suppose. Reduce of empty array with no initial value. Okay, so do I have to provide, where do I provide the initial value? Do I provide it afterwards? Yeah, I do provide it afterwards. Okay, so hello Simon, we do have hello Simon. So in this specific case, we get nothing. If I put 1 in here, there's only one neighboring key. If I put 2 in here, there should be 9 of them. Right, I put 3. Now we have this many of them, 45. It is 45. I can do now 4. Right, and it is in fact 165, right? So this is 5. And as you can see, it's super easy to add additional sort of things, right? So I had 5 nested loops, but since I don't have any nested loops anymore, it's super easy for me to add the 6th one. It's just I just increment the number, right? So I used to like manually add those nested loops. Now I don't have to because I do that through recursion, right? So that's how it works. So that's a very good demonstration of like usefulness of recursion, I think. So the next number is 1287, which raises the question, yeah, it is, look at that. So, and the next one is going to be 3003. We can also check that, right? So it's going to be 7. Let's see. God damn it. Pretty printing. All right, so let's actually do join. Let's do the join. And this is gonna be, yeah, this is gonna be that. 3003, precisely. So what's interesting is that we can't really easily handle all of this, right? So we can't really easily handle all of this because we're just like printing this kind of stuff. It would be nice, in my opinion, if we accepted sort of like the result in here, right? What if we accepted the result in here? So I would say result equal to that, right? So I accept the like empty thing in here, and then I accept the result in here. And instead of printing this entire thing, we would actually push this value to the results, right? There we go. So in that way, after we call this entire recursion, we would have result length, right? So, and then we can iterate all of that, right? Then we can iterate all of that. So push does not work. What? Property of undefined push. Oh, this is because we have to continue like doing it like so. Yeah, no, so and we basically generate this kind of stuff once. We generate all of the neighbors once, and we can reuse that. And this is actually super important for us, by the way. This is actually super important because we need to generate transition rules, which basically state, right, automaton. If we are at the state, and we have neighborhood transitions. neighborhood, we have to switch to the most frequent state, state 1, in that specific neighborhood. So that means we're going to be keep iterating all of the possible neighborhoods over and over again for each individual state. So that means it's better for us to generate the list of neighborhoods only once, right? Just generate the list of neighborhoods only once and just keep reiterating it without like regenerating it over and over again, right? And we're, by the way, generating it in a very slow way, right? Generating like I think 10 is going to take a lot of time already, right? So let me actually. Yeah, so it's look how much time it takes. Right. Is that tail core recursive? No. Okay. So one of the things we can do in here, what exactly can we do? We can cut off some situations when a thing is not like when it's already more than 8 or some stuff like that. So I want to have a shortcut for the sum. All right, x reduce ab. Right, so we want to have something like this because I don't want to type this specific expression over and over again. I want to just say sum, and that's it. There we go. Look how easy it is. So what we can do, all right, if some axis is less or equal than 8, only then we go into the recursion, right? Only then we go into the recursion. So another interesting thing could be actually, yeah, so we don't have to iterate everything. Essentially, we can subtract some axis. Yeah, that's actually kind of cool. Would that be enough, actually? Would that be enough? That could be. So let me maybe do something like this. Because I don't want to recompute it over and over again, right? So if state is less or equal than 0, right, we just check for that and we add it there, and then we return out of this entire step. If we have that, I think that should work actually. I think that should work. Result. This is not result. This is reduce. Yo. I think it worked, but let's actually double check. So we can do something like this. Okay, I can do 0 up until 10. All right. But that also means that we have to clean it up. So we can do something like this. All right, and we can say I length. Okay. And oh, I see. Jesus Christ. Okay. All right, and that looks like the right thing. Right. So this is the right sequence, but it's much faster actually. It's actually much faster. Right. So 11, 12. What about 20? I mean, it's still slow. Yeah, we probably won't be able to use anything but the cute people pixel art, right? So we probably won't be able to use any of that. So we'll get this up from Techno F33L. I think I didn't acknowledge you. Thank you. And K-Mod 9, I acknowledge you. Yeah, I remember it. Okay, so that's fine. So what if I just have 20, right? So just a single 20. How much time a single 20 will take? Well, probably a lot. Not that many. So it generated 2 million neighborhoods. About that. So that's pretty cool. But it was not impossible, right? And we're going to be generating it only once, right? So we're going to be generating it only once. Right, so that's poggers in my opinion. And by the way, since I'm calling sum only once, maybe it makes sense to actually put it like this. Right, I don't know. I think it's needed. So it's a self-contained function, so to speak, more or less. Self-contained function. Right. So I was thinking, can I do stuff like this, where I also return the result? So then I can do stuff like neighbor I without worrying about this thing. Right. So will that work for me? So result length undefined. Okay, I see. So this is probably because here I have to return the result like so. Right. I think it works out. Right. So this is very easy way to define this kind of function, right? Because upon calling it, you create two new arrays. And then as we call recursively, we actually don't create new arrays, we reuse the ones that we created at here. And that actually kind of syntactically makes it the entire function easier to use. Look at that. That's actually kind of cool, isn't it? I think it's cool. Yo. And for this thing, I actually want to make like a single line. Maybe not, I don't know. Just going for aesthetics already. Yeah. So that's poggers in my opinion. So maybe we should call this thing something like neighbor. Neighbors, all neighbors. And the function is ready to be copy-pasted into the main program, right? So let's go ahead to this thing and put it in here somewhere. So frequency rules, I'm gonna put it in here, and I think I wanna put some types in here, right? I think it's quite important. So this thing is a number. This thing is array of numbers. Is it array of? I think it is array of numbers. And this thing is array of strings. That's kind of important. And what we get is an array of strings. Very important. All right. So what we can do now, we can do all neighbors automaton length, right? And it gives us all of the neighborhoods. Neighbors. There we go. All the neighborhoods. So now what we have to do for each individual state, we have to iterate. For each individual state, we have to iterate and switch to the most frequent one. And we need to detect the most frequent one. That's the problem here. That's the problem here. Right, so it would be probably nice to do that somewhere in here, in a place where we actually add this entire thing to here. I think that will make sense. So essentially here we have to iterate all of the all of the axes and find the index of the most frequent one. Right, so that's the problem, because okay, is there any function for that? Right, is there any function for that? So we can ask Mr. Chi to tell us, but it probably will just generate the function from scratch. I can generate it myself, but anyway. How in JavaScript find the index of the biggest value of the array? Is there any standard function for that? Okay, so let me put some stuff in here. Oh my god, this is not... I can't see shit. Why is it so small? Okay. No need to implement it for me. I can implement it myself. Thanks. Right. Because it will probably just... Oh, here's the function. It will just generate this kind of thing. Right. Not the biggest index of, okay. So you're suggesting to iterate array twice. I mean, it's probably not gonna be that big. I mean, you can do that in one go. That's a dumb way of doing it. I don't like this way of doing that. It's not... well, it's still technically O of n. I mean, but... Alright. We can do that, I suppose, sure. Since it's probably going to be like around 100, and we're definitely not going to have like more than 11 anyway, so we can use that, sure. So, okay, here I want to actually put this thing. Right, let's see how it's going to work out. All right, so what the fuck is this shit? Oh, I see. Yeah. So let's actually do something like 10. Right, and console log results. All right, that's cool. 9. Is it a good one? 10 carry. Okay. All right. So, but that actually means that this function is not this function is not what it claims to be. All frequent neighbors, or maybe all neighbors fricks. That's a better one. Let's go back to here. Okay. So what do we have in here? It's going to be number. So then here we accept the array of numbers, and here is actually array of pairs. So the first one is the string, the second one is the index, right? So this is basically what we have in here. And we're going to get this thing in here. So what I want to try, what am I looking at? Did I? Okay, what? So I don't need this thing anymore? Okay. I feel like... What did I remove? Am I going crazy? So this is neighbors. Frac rules. I removed frac rules. What the fuck? Wait a second. I removed frac rules accidentally. This is important. Yeah, here it is. Oh my god. Ooh. Alright. So let's remove this thing. So let's go back. Then this is going to be number. What is it called? What it is? It's a string and number and this thing. Okay. So and then I accept this stuff and return that stuff. Okay, cool. What I want now is just double check if this compiles, if it matches the types. I'm pretty sure it should, but we'll see. Okay. So all neighbor frex. Okay, frex. Neighbors frex. So now this is very important thing. Okay, so we're iterating through all the states. Right, automaton length. Right, these are all the states. For each individual state, automaton being at that specific state, we encounter one specific neighborhood. Can you do something like neighbor frequency, neighbors frequency, right? If at state I encounter neighborhood neighbor, I switch to the most frequent one in here. That's what I do. And that's it. So that's the whole thing. Yeah, believe it or not, that's the whole thing. So iterating through all the neighborhoods, right? So when we pick the one that is most right, the most frequent. So let's try to compile this entire thing and see. Okay, so we have here. It has to be something like off. I see. Okay, so let me see what we've got. So we are using cute people. Okay, we create the frequency rules. We can try to print them, but it may actually take a huge amount of time. So though we're not gonna have that many of them. Okay, so let's actually try to print them. Let's try to print them. Okay, so at the state 1, here are the transitions. That's a lot of transitions. Well, I mean, it's not that many transitions, but it's a lot for the yeah, for the poor Chromium, or for my poor laptop. I literally have to close that page because I cannot display that. That's how old my laptop is. It can't display this shit. So maybe, yeah, so maybe the whole logic should have been written in WebAssembly, right? For my laptop. Anyway, so let me double check this kind of stuff. Show me DevTools, please. I'm gonna refresh one more time. And now let's try to compute the next state. And they're basically disappearing. So yeah, they end up basically disappearing. Right, if we try to play this kind of thing. But it's actually kind of cooler. They're disappearing in a cooler way, I think. They're disappearing in a cooler way. So, alright, let's maybe try tsodinPog. I don't know. Though tsodinPog, it may take a lot of time to generate the states, because there are going to be a lot of states. But we'll see. Maybe that's going to be fine. Yeah. Let's wait a little bit. Let's wait until it maybe generates some states. How would it look if we just calculate the frequencies only once for the first step? We do not compute frequency for any of the steps. When we're simulating cellular automatons, we're not computing any frequencies at all. At all. Well, I mean, technically we do, but I mean, that means I don't understand exactly what you mean. Right. So the whole process of this neighbor's frequency stuff, it happens at the step of building transition table. This function is never called anywhere during the simulation at all. Completely. We don't even touch this function there. It's only when we generate transition tables. Okay, so it's too it's too difficult for this thing. So that means I don't really understand what you mean, like compute frequency only once per step. I don't understand what you mean in that case. Okay, so right. So all right. Yeah. All of the cellular automatons end up basically collapsing, but they're collapsing in different interesting ways. I think, okay, so the most interesting one is probably was cycling. Yeah, cycling is actually kind of cool. Right, so let's actually take a look at the cycling. Right. So let's take a look at the cycling. And yeah, they explode, essentially. And they keep like having like a static noise and stuff like that. Right, so right, but if we use the frequencies, right, if we use the frequencies, they collapse instead. Right, they collapse instead. All right. And they were just like going down. So it's kind of cool. Really like that. So depending on how you analyze the images and how you generate different transition tables, it just like ends up being different. Yeah. So that was an interesting project, I think. I think that was an interesting project. I didn't really achieve, like, the results are interesting, right? So if you analyze these things different ways, you get different effects, which is kind of cool. But to be fair, I was expecting something more spectacular, right? So expecting something more spectacular, but I'm really glad that I did this thing anyway, right? So this one is also kind of fun. They're disappearing, but they're disappearing differently, right? So, but this kind of thing actually taught me a lot. I tried a lot of interesting things, right? This is something that I always wanted to try. So I guess this is going to be the last episode of this entire Autocell thing. So let me pick, maybe, let's actually keep Metldown. And let's commit whatever we have already. Maybe I'm going to actually recompile this entire stuff. Compilation. Implement, what do we have? Try different ways of generating transition tables. Yeah, transition tables. I'm gonna push that right into the repo. All right, so isn't that poggers? I think that's pretty freaking poggers. I guess that's it for today. Thanks everyone who's watching me right now. I really appreciate that. Have a good one, and I see you on the next Azurzin session. So yeah, love you all.